Hello everyone and welcome to Alternative Math, the series we do where we take common high school or college math questions and give you by the book and alternative methods for solving them. Today's question is the integral from -1 to 1 of the square root of 1 minus x squared dx. And anytime you have an integral of the form square root of a squared minus x squared, you should automatically think trig substitution, and that's what we're going to do here. So, trig substitution is when you replace the variable you have with a trig function. For this case, I'm going to select my x to be equal to sine of theta. And we have to replace the dx. That's just taking the derivative of sine theta, which is cosine theta. And then we add on a d theta. And now, with this, we can replace the bounds. And so we need to replace the upper and lower bounds. And the way we do that is to determine sine of theta is equal to 1. So we're going to do the upper bound first. And what theta value, such that the sine of that theta value will get you 1. And we know by the unit circle that that is theta is equal to pi over 2. And now for the lower bound, we ask a similar question. What theta such that the sine theta is equal to -1? And we know that by the unit circle as well, theta will equal negative pi over 2. And now we can just rewrite our integral in terms of these bounds and these trig functions. And so we now have the integral from negative pi over 2, we're plugging in our bounds, negative pi over 2 to pi over 2, of the square root of 1 minus, now x equals sine squared, or x equals sine theta. So I'm going to replace the x squared with sine squared theta. And at the end, we had a cosine theta d theta. And we do this because now, inside the square root, we have a 1 minus sine squared theta, which we know by a trig identity is equal to cosine squared theta. And so now we have the integral of the square root of cosine squared theta, and that just becomes cosine theta. And then we have to add on this cosine theta d theta, so you have cosine theta times cosine theta d theta, or if we rewrite our integral, we can combine all of that to become the integral from pi over 2 to negative pi over 2 of cosine squared theta d theta. And now I'm going to use another trig substitution. This one, cosine squared theta is equal to cosine 2 theta plus 1 all over 2. And so we do that because that's even easier to integrate than cosine squared 2 theta, or cosine squared theta. So now, when we plug in our substitution, we have negative pi over 2 to pi over 2 of cosine 2 theta over 2. And now I'm going to break apart the integrand d theta into two integrals from negative pi over 2 to pi over 2 of 1/2 d theta. Alright, let's deal with the integral on the left first. So we're looking for a solution to the integral from pi over 2 to pi over negative pi over 2 to pi over 2 of cosine 2 theta over 2 d theta. And now cosine, the antiderivative of cosine is sine, so let's write that down. And the antiderivative of cosine 2 theta would be sine 2 theta. And then with the reverse chain rule, we would divide by 2, and since we already have a 2 in the denominator, that becomes a 4. Now let's plug in our bounds. pi over 2 and negative pi over 2. So when we plug in pi over 2, we get sine of 2 times pi over 2, which is equal to sine pi. So we get sine of pi all over 4, and then we subtract away sine. When we plug in negative pi over 2, we get sine of negative pi all over 4. But sine of pi and sine of negative pi are both 0, which means both of these go to 0, and our original integral is 0. Alright, now let's tackle the integral on the right, which is an even easier integral to do. We have the integral from negative pi over 2 to pi over 2 of 1/2 d theta, which the antiderivative of 1/2 d theta is just theta over 2 when we evaluate at pi over 2 and negative pi over 2. We get, when we plug in pi over 2, we get pi over 4, and then we subtract away negative pi over 2 over 2. So we're subtracting away negative pi over 4. And then we arrive at our answer, which is pi over 2. Which is great, and that's the by-the-book way of doing this integral. Now let me show you an alternative way of doing the integral, and the alternative way is to recognize that our function inside the integrand is actually the function of a half circle of radius 1. And we can see that if we take the equation of a circle, which is y squared plus x squared equals 1, if we solve for y in this equation, we get and move the x squared over to the other side and then take the square root of both sides, we'll get y is equal to 1 minus x squared, which is our function inside the integrand. So if we draw our function, we'll see that it's just the upper half of the unit circle. It's only the upper half because we now have y as a function of x, and if we included the lower half, it would violate the vertical line test. And so an integral is just the area under the function, and that's all this area here. The area between the circle and the x-axis. Well, that's just the area of half a circle. So we can just use the familiar formula pi r squared. Here our radius is equal to 1, and so we're left with pi, but since we have half a circle, we just divide by 2, and we get the exact same answer 2 different ways.